Tonight, I'm delighted to be able to introduce to you Richard Bonomo. And he told me that that's how you pronounce that because... Do you want me to say or do you want to tell us? Okay, so it's actually buono uomo. And having been in Italy, and now I'm affluent in Italian, that means...
Good man.
Good man. And it's like, he was born in Yonkers, New York. You know how I tell everybody, each speaker I say where he's from, where they went to high school? He's smashing the record for the most high schools ever. So he first went to San Diego, the high school associated with the University of San Diego. Then he went to the American School in Kuwait. And then he went to the American International School in Vienna. And then he went to the high school associated with Camp Lejeune in North Carolina. And you can tell who his dad served with. Okay. And then he got his undergraduate degree at Case Institute in Cleveland, and he got his master's here and is working on his PhD in fusion. And I've avoided making any jokes about confusion, but I had to do that. So we get to hear about controlled nuclear fusion research here at UW-Madison. It's going to be pretty interesting because he's going to talk about the terrestrial and then the extraterrestrial. As I said in my little missive, it's amazing how little, I had to look up a lot about fusion because it's just not there. And so I'm really looking forward to, in about an hour, knowing a lot more about controlled nuclear fusion research. Please join me in welcoming Rich Bonomo to Wednesday Night Talk.
Thank you very much for coming out tonight. I hope there we go. Can you hear me now? Okay. Thank you very much for coming out tonight. I hope your time is well spent this evening. Again, my topic is nuclear fusion research at the University of Wisconsin-Madison, the present and the terrestrial, the future and the extraterrestrial. I'm not from Wisconsin originally. I've been here for almost 40 years, so it's home now, has been for a while. I knew it was home when I bought my burial plot. But I've always been amazed at what has come out of this university located in the middle of nowhere in particular. Because really there's no reason to have a city and a major university here, really. No major seaport, nothing. But it's here. And I've also been amazed at how much stuff has come out of this university which has so greatly benefited mankind and had such a positive influence on human life. For example, as most of you probably are aware, the process for putting vitamin D in milk was developed here. Warfarin, which is a blood thinner, which is used both in rat poison and in medical blood thinner called Coumadin. It really instills confidence, doesn't it? Was developed here. And also the entire field of space astronomy was developed by Dr. Art Code, may he rest in peace, he died some years ago, here at the University of Wisconsin. Space astronomy is that field of astronomy where observations are made not from the ground, but from orbiting platforms high above the atmosphere, sounding rockets, satellites, and so forth. So you can see, image things or see things or count photons in wavelengths and bands which simply cannot get into the atmosphere because the atmosphere blocks them. And this is a revolution in astronomy which is on a par with Galileo turning a telescope on the sky for the first time and seeing things which no man had seen before. It's not fully appreciated yet because we're in the middle of it, but 500 years from now, when they write the textbooks, that accomplishment of this field, the found of this field, is going to be on the same par with that, and the historians are supposed to be saying that. And it came from here. And there are not many other things which have come here that I don't know about or haven't been noted yet, but they're there for sure. I'm saying this because what I'm going to describe tonight at some point is a similar thing. I'm going to tell you about something which is going to change the future of mankind in a very dramatic and I hope positive way, and it's going to affect every man, woman, and child on this planet. I hope for the good. Now, before I get started, I'd like to say a few words about symbols. Every field has its symbology system. All right, architecture has things it puts on paper to represent things. Classical religious art will have figures of in flowing white robes with wings, or people, glowing rings around their heads. And of course, these stand for something else. I mean, the flowing robes, the wings are angels. We all know that, but of course, they don't have bodies; they're non-corporeal. But so you have to represent them somehow. So that's the way you do it. People who are known for their holiness, you put a ring over their head so you can mark that. They don't all go walking with glowing rings over their head normally, right? So here we do something similar. You're going to see a lot of these things on my diagrams. Circles, nice little billiard ball things representing protons, neutrons, deuterons, tritons, atoms, and so on and so forth. It's very important to know that even though we draw these pictures and even talk about these things in this way, nuclei, especially of large atoms, are not made of marble stuck together. All right? This is a model, something we can draw so we can have somebody refer to it and talking about it. Remember, it is always bear in mind that symbols are convenient representations of particles. They do not resemble the particles. For example, the deuteron here is a proton and neutron. And as far as the nuclear physicists can tell, it's shaped more like a football than two spheres stuck together. The triton and helium atoms, I believe, are spheres in terms of their geometry. But for the sake of convenience, we draw them like this. Just keep that in mind. I don't want to have you confusing the symbols with reality, right? And that can be a problem sometimes, especially dealing with something with which you're not familiar. Now, the nuclear fusion process, to speak about this for a bit, works as follows. Now, I'll take advantage of this. We'll use the sun's nuclear fusion process because it's there. We all see it. Our sun is of a size and mass such that it burns hydrogen. Not all stars burn hydrogen. Some burn helium, some burn heavier elements. But our sun burns hydrogen, the lightest of elements. So what we have is hydrogen atoms. They're located deep in the sun. Of course, they don't really exist as atoms because the electrons get stripped from the atoms, so they're sort of floating on freely, but the charges still add up. The four hydrogens go through a fairly complex nuclear fusion process, which I won't go through, and I probably don't know anyway. And out pops at the end the helium if it goes all the way to completion. It does not always go to completion. Sometimes this process gets terminated halfway and things get expelled from the sun. I'll mention that later. Well, it turns out that if you add up the masses of the four hydrogens, you get a number. And if you look at the mass of the resulting helium, you have another number. And if you subtract them, there's a difference. This difference in mass is the energy that's released, usually in the form of the kinetic energy of the resulting product. That little number, if you multiply by the famous equation of Einstein equals mc squared, so m is a very small number, c squared is a large number. The speed of light is 186,000 miles per second, or about 30 million meters per second, or 30 megameters per second, to use the correct term. So you can get quite a bit of energy out of a small amount. Now, fission reactors of the sort we already use work in sort of the opposite way. You have very heavy elements like uranium and plutonium. They split, and the same thing occurs that if you calculate the mass of the products, you discover the mass of the products is less than the mass of the reactants, the original atom, and that is released as energy. And that's how nuclear energy more or less works. So the fusing of very light elements produces energy. The fission of very heavy elements liberates energy. And apparently these two things meet at iron 57. So apparently iron 57 has the most efficient nucleus and has no energy release. So I guess floating around in the cosmos, there are actually stars made of iron because they have used up all their fuel and fused as far as they can, and they're stuck. If they're the right size, they'll just stay that way. Now, the reason we're doing this is because we're beating our heads against the wall trying to do this is because we are coming up with an energy crisis. I just pulled this thing from the web. They're one of many such things, which simply show that if you extrapolate from our current energy consumption and population growth and such and our current estimated supplies of fossil fuels, you're going to get to a point where the fuel demand is going to outstrip the fuel supply. And it's not too far in the future. Now, where this is not really fixed, that there are various theories. But the fact is, it is finite regardless. Now, I will also point out that there's a lot of talk about global warming. whether or not man is causing this through the use of CO2 or not. From my perspective, it doesn't matter. We're going to run out of fossil fuel. Sooner or later, we're going to run out of fossil fuel. So if we don't choke ourselves to death or fire ourselves to death, we're still going to run out. So even if it turns out that anthropogenic global warming is not an issue, we still have a problem. All right? We cannot survive for the distant future burning fossil fuels for many reasons, one of them being there simply aren't enough. So here is a slide which sort of illustrates why fusion researchers continue to strive to make this happen. This is a slide of some of the possible fusion reactions that could be done. And where's my light? It's okay, it's a little fainted here. I think the battery's dying. So resort to the pointer. So this is deuterium, tritium. Okay, so deuterium is an isotope of hydrogen, 1 proton, 1 neutron. Tritium is a heavier isotope of hydrogen, 1 proton, 2 neutrons. Helium-3 is an odd isotope of helium. Instead of having 2 neutrons, it has 1, so it's kind of a light version of helium. And if you take 100 cubic feet of each of these gas mixtures, so just imagine a box that's 100 cubic feet, 10 feet by 10 feet by a foot high. It's not a big volume. It's a pretty small volume, right? If you were to fuse all the gases in those boxes through this nuclear reaction and then get the energy out, you'll discover that 100 cubic feet of deuterium, that's 100 cubic feet at atmospheric pressure and about 32 degrees Fahrenheit, you're going to get the equivalent of 19 million cubic feet of natural gas, okay? This is a dramatic difference. Or if you prefer 162,000 gallons of heating oil or 3,600 barrels of crude oil and so on and so forth, you can read it there, 753 tons, US tons of coal. Similarly, if you use these other combinations, deuterium and tritium, you'll also wind up with very large numbers. So with a very small amount of material, you can generate and liberate a lot of energy. And that's why nuclear fusion is so attractive. And that's why we must make this work somehow. So energy is one of the major reasons for pursuing nuclear fusion research. In fact, is the biggest reason. But there are other reasons as well. One of them is to have neutron sources. So if you fuse deuterium and deuterium, you get, let's see, I think there's an animation here, maybe not. You get neutrons out. Deuterium and tritium, you get neutrons out. And these have various energies. Now, if you look here, I have the energy of these reactions noted in MeV. This is million electron volts, and I'm going to explain that in just a few moments. So this is another reason we're trying to work on fusion. More about this later. Now, at the University of Wisconsin, we have a very large fusion program, one of the largest in the country. That's why I came here, actually. It's spread over 3 departments: physics, electrical engineering, and electrical computer engineering. And we used to be called nuclear engineering. It's now called engineering physics. This is a list of the PhD candidates that have graduated, not a list, but a summary in terms of numbers added up. So as of 2014, we had graduated over 160 PhDs in the various aspects of fusion research. And of course, since then, quite a few more. We haven't updated the graphic in a while, my apologies. So this is a large contribution to the world fusion effort coming right here out of this university here. At the university, there are 3 what I call major plasma magnetic confinement devices. There's the Madison symmetric torus in the physics department in Chamberlain Hall, which is classified as a reversed field pinch, which is a type of magnetic confinement device. Unfortunately, the funding for this is now drying up, and I don't know what its future is going to be, or if there'll be something to replace it. We can only hope. There's the heliocentric experiment in the electrical engineering wing of the engineering main building, which is classified as a stellarator device, which is a fairly complicated coil set to hold a plasma in place very stably, and has advantages of some sort, which I won't go into here because it's too complicated for this presentation. But I will point out that this experiment is one of the more innovative plasma physics experiments, plasma confinement experiments, because it is actually designed from the plasma out. In other words, we said, what does a plasma want to see? how can you build a modular device that's something that does not has continuous coil, but has modular coils, which will maximize plasma confinement, and that's how this was designed. Unfortunately, it wound up with the coil set from hell and the vacuum chamber from hell, but it works. There is a larger experiment that is under construction, I think now finished in Germany, called the Wendelstein 7X stellarator, which is designed along similar lines and is larger. Then finally, the Pegasus toroidal experiment, which is a compact tokamak located in the Engineering Research Building, that ugly 13-story tower across the street in the basement, which is also doing quite a bit of pioneering work in this field. So this is now, but all these experiments, though, are primarily oriented toward providing an understanding of the physics that will be needed to design and build nuclear power reactors. So they are physics experiments, okay? We're trying to understand with these experiments, how you hold the hot ionized gas in place with magnetic fields. You have to use something to keep the gas from touching the walls, because it will either quench the reaction or will burn out your walls, one of the two, depending on how big the machine is, both of which are bad. So this is understanding the physics of confining and heating these plasmas, all right? So that's a particular approach to fusion, which this university specializes in. I belong to the Fusion Technology Institute, which does not deal so much with the fusion of the physics of fusion and plasmas, but it deals with the technology aspects. Okay, once you have these things built, how do you make them economical? All right. So there have been studies of the engineering and economic aspects of proposed nuclear fusion reactor designs. You have this reactor. How much secondary waste is it going to produce? How much electricity cost? What kind of waste disposal things do you have to deal with? What are the engineering considerations in building this? How do you cool it? I mean, there's a whole bunch of engineering considerations in building an actual fusion reactor, which you don't worry about when you're doing a plasma physics experiment, all right? But this has to be done before you can actually build these things and make them work in an economic fashion. It doesn't do any good to build, spend $500 or $1 billion on a large fusion reactor, plug it in and have it generate 5 watts, right? It doesn't work, even though it's past break even. And we also, which is a little more innovative and unusual, we developed devices and processes using nuclear fusion for near-term applications. So nuclear fusion power is, of course, all from the future. We always keep saying it's 50 years in the future, always 50 years in the future. I think that that will no longer be true. It's actually gotten to the point now where actually our private companies working on building fusion reactors and designing them using private capital. That's a very good sign. But the very near term, we are, my particular research group deals with inertial electrostatic confinement fusion research, and we have an orientation primarily to very near-term applications. And our laboratory specializes primarily in the deuterium-deuterium fusion reaction here. For various reasons I'll continue to go into. We don't do deuterium-deuterium fusion yet. We might in the future if circumstances warrant, but we don't need to for what we're doing. We're sticking with deuterium. Now, a quick aside here. I keep using these terms, showing this term called EV, and I think I should explain what that means. An EV, that stands for electron volt. All right. If you take a charged particle like an electron, and it goes through a set of rings like this, for example, 2 electrodes, one is negative and the other is positive, it will get drawn toward the positive electrode and speed up a little bit, okay, like that. And when it does that, it picks up some kinetic energy, all right? The amount of kinetic energy is quite small, but we call that an electron volt, all right? So a charged particle, which is accelerated through a 1 volt potential, is said to have acquired 1 electron volt event of kinetic energy, all right? An electron volt is equivalent to 1.6022 times 10 to the negative 19 joules. Remember that number. Well, don't have to remember that number. It's a very small number. It's a 0 followed by a decimal point, followed by 18 zeros, followed by 16022. So it's a very tiny number for 1 electron. But that's what the number means. It's a measure of the kinetic energy that's picked up by the particle. So we have these, so we want to design neutron sources using this reaction because the neutrons that can be produced are attractive. You see that neutron up there has an energy of 2.45 million electron volts. Right? deuterium-tritium reaction has an energy of 14 million electron volts. Keep those numbers in mind. That's important. All right. Now, what do these mean in practical terms? So a neutron with an energy of 2.45 million electron volts has an approximate speed of 13,000 miles per second, or if you prefer metric, 22 million meters per second. Right? It's fast. A 14 MeV neutron has a speed of 52 million meters a second, or 32,000 miles a second. So in 1 second, it's zipped more than one time around the Earth. It's moving out. Very high speed. Now, high-energy neutrons are good and bad. So the bad and the ugly of high-energy neutrons. You get radio, if you're trying to build a nuclear fusion reactor and you're using a deuterium, but especially deuterium-tritium reaction, you have these high-energy neutrons flying around inside the machine, banging into things. You get radioactivation of the structure. Okay, so once you've run the thing for a while, not very long, the whole inside becomes radioactive. Right? Now, when that happens, you can no longer send in a technician to do anything. So if something breaks inside the machine, if you have to replace a wall panel or anything, an antenna structure, you have to do it remotely. When it comes time to take the thing apart and put it in storage for a while, maybe 100 years or so, you've got to do it remotely. You can no longer handle the machine. That's really a pain. Also, neutrons really can mess up structural components and internal components. When they were building the first nuclear fission reactors, they discovered this, that they'd build a test reactor, they'd run it for a while, and the welds were swelling, metal was swelling, things were falling apart because the neutrons were having a bad effect on the metals in the structure. And they had to go do quite a bit of metallurgy to find metals that would actually last for a while under this bombardment. You also get heat deposition in inconvenient places. So you have a wall here, neutrons flying through. Well, most of them actually fly through the first layers or so, because neutrons don't interact with matter that much. They're neutral particles. So they actually have to bang into things to actually transfer kinetic energy. There's a large number of them, so it happens. But the fact is you can have something here, the wall, first wall getting hit. You can have something way back here, behind some shielding even, and it's still getting neutron bombardment, so it's getting hot. And that's really a pain, honestly. Plus you have to have massive shielding required for personnel and environmental safety. So if you have, for example, if you look at nuclear power reactors, there's always this massive amounts of concrete shielding around things. Has to keep the neutrons from getting out. And that, of course, if you're adding shielding, it adds to construction cost. If you're trying to design something which is mobile, it makes things very difficult. For a time there, in the late 50s and early 60s, they actually tried to build consider building a nuclear-powered airplane. And we actually built an aircraft with a nuclear reactor on it. It didn't power the plane, but it was just there as a sort of a test. So they took off and flew with this thing, massive shielding between the reactor and the crew, of course. And behind that was another plane following with a whole bunch of U.S. Marines aboard, so that if this plane crashed, these Marines would jump out of the plane in parachutes and form a security cordon around the thing. The Soviets actually built a functioning nuclear power airplane, actually flew the thing. And unfortunately, the crews, I think, died of radiation poisoning. So it can be done, but it's really kind of hard to do with these neutrons. So that's the bad and the ugly of neutrons. But there's also a good side. Neutron sources are useful. Of course, you don't want quite the flux of neutrons, the quantity of neutrons you have with power reactors, but they are useful. For example, the manufacture of radiopharmaceuticals can be done with neutrons. I'll go into that a bit more later. There are various neutron-employing medical treatments. You can do detection of smuggled nuclear materials. You can do detection of chemical explosives. You can manufacture solid-state devices. You can do neutron radiography, and there are other things too. So the list goes on and on. So neutron sources can be very useful, and there's actually many applications for them. So again, we tend to focus in our laboratory on the deuterium-deuterium reaction. For one reason, deuterium is stable and not radioactive. So if I have a bottle of deuterium sitting here, it poses no radiation danger. It's completely stable. Right? And there's no licensing required. If I had a bottle of tritium here, the UW safety people and the state radiation safety and licensing people would probably have something to say about that. But deuterium is completely stable, and non-harmful in that respect. It's just hydrogen. Now, the nice thing about this is it means you can have a neutron source which is not inherently radioactive, and it's just sitting there, right? So we have various laboratory apparatus in our laboratory located in the engineering research building underneath the porch. Underneath the porch, in one section, it's surrounded by 4-foot-thick concrete walls to absorb neutrons. I think it's the only neutron bunker on campus. But we have these devices which are used to do inertial electrostatic confinement fusion research. The workhorse device is called Homer. I have no idea why it's called Homer, but it's called Homer. And that is the workhorse device built from scraps. This machine this vacuum chambers had many identities, various configurations for electrostatic confinement diffusion devices, also built from scraps. Helios is the one machine that was actually built by a vendor for our tour specifications, also before my time. But this machine has the distinction of being the first device in which helium-3 fusion was conducted outside of an accelerator. And we'll go into that helium-3 fusion business a little later. This is Luna, which is under construction. This is going to be kind of a linear neutron source. And Ping was proposed by a grad student by a Craig Schuffner group. May he rest in peace. He passed away while he was getting his degree. He was given his degree posthumously. It's a very innovative device. I hope we can still build it somehow, depending on funding and many other things. Now, Homer, I'll use this as the example because it is the workhorse device and sort of typical. It has a high voltage feed through and a stalk which connects to a spherical grid, just a wire grid, in this case made of tungsten-rhenium alloy for its heat properties. That is surrounded by another grid made of stainless steel wires, which is connected to the tank. The tank is connected to Earth. This is connected to a power supply which provides very high-value negative voltage. Our power supply in our laboratory can supply negative voltage from 0 to 300,000 volts negative. So again, the anode, the ground potential, the cathode is negative. This is a little old. We can actually get much higher than this in theory, but we don't tend to push it because we're still making the modifications necessary. We have filaments in these machines. These are stuck inside the machine on electrodes. These filaments are ordinary light bulb filaments. You literally buy light bulbs, we smash them open, pull the filaments out, and we put them in the machine attached to electrodes. Anything we do to save money, right? But so then once, whoops, I think I may have. Okay, then the deuterium gas is then pumped into the chamber. So it's now floating free in this vacuum chamber at a low pressure. And then the filaments kick off electrons. So we heat the filaments up, we bias them negative, we kick the electrons off of the filament. The electrons kind of boil off. They go into the gas, hit the gas, and ionize some of the gas. Then the gas forms ions of various sorts, positive ions and free electrons. Then with the high voltage, negative voltage on the central electrode, these free positive ions will drift in between these two electrodes and suddenly see a steep, what we call a steep potential hill. They'll see, quotation marks, this very negative thing sitting over there, and the Coulombic attraction will cause the positive ions to accelerate toward it. So they'll accelerate toward this grid, pass through it, pass out the other side, slow down, turn around and come back. So in theory, these positive ions are going back and forth, and as they do, they smack into each other sometimes, and you get nuclear fusion. And that will give you showers of neutrons and other particles. So this is kind of neat, because you can take deuterium gas, which is not radioactive, you can put it in this machine, which is a very simple machine. I mean, this is a very simple device functionally. And you get neutrons. You turn it on, you get nuclear fusion. You turn it off, fusion stops. You turn it on, you get nuclear fusion. You turn it off. It's really neat. I mean, it still amazes me that you can do this at all. So now we have a way of producing neutrons fairly easily. And of course, one of the things you need to do is try to figure out how to make more neutrons for given energy and that kind of thing. But then we can do all sorts of things with them. So, for example, some years ago, the IC group graduate students demonstrated the production of certain medical isotopes over 10 years ago using DD fusion neutrons. So using these neutrons, he's able to demonstrate the production of fusion neutrons and the production of medical radioisotopes, which I'll explain more later. Now, two of the graduates have formed two companies which are in the area. There's Phoenix Nuclear Labs, which produces these DT gas target neutron sources. They use tritium, and what they do is they actually produce a beam of deuterium and fire it into a blob of tritium gas to produce neutrons. Shine Medical using these sources to produce various medical radioisotopes, especially technetium-99, and that's rather important. I'll go into that a bit more, I believe, later. So molybdenum-99 is widely used as a medical diagnostic, and it is being produced via induced fusion. So you have an incoming neutron from some source, it bangs into a uranium atom, and you get Moly-99 as one of the products. Okay, and this is what you're looking for. The Moly-99 then decays, I believe, into technetium-99. Now, we've been getting this for many years from certain nuclear reactors in Canada, nuclear fission reactors in Canada. They've been well beyond their original intended lifetime, and they've been used well beyond their intended lifetime, specifically to produce this radioisotope. Well, it's just gotten to the point where they can no longer be safely operated. You can only use so much baling wire and duct tape to keep one of these things going safely. So the scramble was on to find other ways to produce this medical radioisotope, which is a very commonly used medical isotope. And that's how our students 10 years ago started working on this problem as they saw this coming. Now, it can also detect smuggled nuclear materials if you have a neutron source. So you have an incoming neutron, it bangs into uranium-235, which is a fissile material, and it lets off products like molybdenum. It also lets off these neutrons, which are immediately generated as a consequence of this induced fission reaction. And then later on, you'll have some of these other fission products will produce additional neutrons. So if you send in a pulse of neutrons, then you kind of look to detect neutrons coming out. You can just tell whether or not there's a fissile material there. And this has practical applications also. Also detection of chemical explosives. If you send a neutron into a target atom, nucleus, it captures it, and then the nucleus decays in various ways and sends off gamma radiation and other particles. The gamma radiation that it sends out will depend on the identity of the nucleus. Different nuclei, different species of elements, different elements will produce different spectra of gamma radiation. And this is, I believe, called nuclear activation analysis. And from this spectrum of gamma rays, you can determine what the original nucleus was. Well, it turns out that a lot of common explosives, such as RDX, nitroglycerin, and trinitrotoluene, happen to have a lot of nitrogen. So if you do this process on something and you get a lot of nitrogen gamma rays, then you can suspect that there's actually a chemical explosive in the thing, in the object that you're scanning. Now, as you know, we live in pretty terrifying times, in that there are a lot of people who want to hurt people, and they want to bring fissile materials in to do nasty things and bring explosives into nasty things. We have a lot of ports of entry in the United States and other countries too, and the question is, how do you look for this stuff? Right? You cannot stop every vehicle and take every package apart that comes into the border without making the economy stop. It's cold. So you have to have ways of scanning the stuff, try to find likely targets where people might be trying to smuggle in fissile materials for illegal use, or I should say murderous use, or explosives. So this is one concept that we came up with here at the university, where you'd have a building at a portal crossing. You'd bring in a shipping container. This is for trucks, of course. In this case, you bring in the shipping container, and then here you would have neutron generators producing pulses of neutrons. Okay, just they go through everything. And then if there's, say, some fissile material or some explosive buried, hidden in some object inside one of these shipping containers, then the idea is that as it produces its neutrons or gamma radiation, then the sensors located near the container would be able to pick them up, we hope. And then if you get a positive signal, that container would then be shunted off to the side and unloaded and inspected more thoroughly. All right? So this is one application, and this is something which is, frankly, kind of critical that we're trying to develop. Right now, our portals are using passive sensors to try to pick up radiation, which is, of course, less effective. But we're doing what we can do. Homeland Security is doing what it can do, and so is security in other countries. One proposal that was made by members of our group is to try to take the same technique and use it to try to find IEDs or buried nuclear materials. The idea here is that you would have on this copter drone a neutron source, which would be scanning the ground. And well, let me just kind of let the animation go. So you'd have a truck here with a power source sending microwave radiation up, and it would be targeting a data and power relay drone here. This would receive the radiation from the truck. It would be used to power the propellers, and then re-radiate microwaves down to the drone here, which would have the neutron source. This is scanning back and forth, sending neutrons into the ground. And then you'd have other drones around it with detector apparatus looking for the return neutron or gamma ray signal. So the idea would be to use this particular arrangement either in potential combat zones where you have a formation of troops going down a road and you want to be able to look for buried explosives in front of the column of troops, or if you are trying to clear a minefield. A huge number of people are still getting killed and maimed by buried mines, especially children. And finding these old minefields dating back to World War II sometimes is a challenge. And this would be a very good way to try to find those mines that are still dormant and sitting underground, using something like, using a variation of this. Now, let's go to the topic of helium-3 fusion. Helium-3 fusion involves fusing two helium-3 nuclei. Again, it's two protons and one neutron. And then getting out these other products, protons and helium-4, which is the regular version of helium we use to blow up balloons. And that comes out with an energy of 12.86 MeV, which is a fairly decent amount of energy for one reaction. Nice thing about this is that there are no neutrons at all. This reaction is completely aneutronic. Right? And this has many advantages. There's no nuclear waste at all, so I mean, with the DT fusion, even though the products of the reaction are not waste, the irradiated structure, the radioactivated structure would be a form of waste which had to be dealt with. It's not as bad as the strontium and other things that come out of nuclear fission reactors, but it'll still be a pain to deal with. You'd have to put things stuff away for a couple hundred years. Not 100,000 years like fission products, but just a couple hundred years we can handle that. But this, not even that. You would have no nuclear waste at all. You also have no inherent need for a heat cycle. When you have a lot of your energy coming out as neutrons, as you do with fission reactors or you would in a deuterium-tritium fusion reactor, the only way to convert the kinetic energy of the neutron into useful energy to generate electricity or whatever you want to do with it is to let it bang into things and transfer its kinetic energy into some bulk material and heat it up. Then you can use the bulk material to heat water or something to spin a turbine or something to generate electricity. There are various ways of doing it. But you have to go through a heat cycle. Heat cycles have an inherent inefficiency. I believe it's called the Carnot inefficiency, and you cannot really get around that. So as soon as you start going to a heat cycle, you're stuck. Let's see. And so you don't have an inherent need for a heat cycle because all the particles coming out of this reaction are charged particles. So when you have a moving charged particle, you can send it towards something, and it will induce a current in the electrode or whatever you have going into. And so you can actually directly convert the kinetic energy, the movement of the charged particles into electricity. So in theory, there's no limit on your efficiency. You can go up to about 100%, in theory at least. What would actually happen, of course, is probably not. There's one disadvantage, however. Helium-3 does not occur on Earth in useful quantities. Does anybody know where we get our helium-3 from nowadays? Anybody know? Okay, it's extremely rare on Earth. We get our helium-3 supplies that we use for research purposes and for and medical diagnostics and for cryogenics from decaying nuclear weapons. So we have the stockpiles of nuclear weapons. Some of them have tritium in them to increase their output. The tritium is a radioactive gas which decays. It decays into helium-3. So every so often they have to go from warhead to warhead or bomb to bomb, pull out the helium-3 and put in new tritium, if there's any tritium to be put in. I don't even know if they have any tritium anymore. And that is how we get our helium-3. We're actually buying it from the Russians for a long time too, but there is no natural source on Earth for this. As a consequence, when once Homeland Security became an issue and you had to start looking for bad guys bringing stuff in, a lot of the helium-3, almost all the helium-3 was getting pulled into Homeland Security applications, and of course that meant that the price went up. When I first came here, it was kind of here. It was expensive, but not horribly so. And it started rising extremely quickly. As of a few years ago, it was at, what is that number? $3,000 for a liter. And it's a lot higher than that now, I'll tell you. It's almost impossible to get. So the question is, from where else might we be able to get this wonderful fusion fuel to use in the future? Well, back in 1978, some enterprising folks in Britain came up with the idea for Project Daedalus. Project Daedalus was supposed to be an interstellar craft powered at least in part by helium-3. The idea was to send this thing out to Jupiter along with some support ships that would be balloons that would go to Jupiter's atmosphere and pull out, mine helium-3 from the atmosphere of Jupiter where there is a fair amount, and then it would fill the tanks on this ship, which would then fly to Barnard's star, about 50 light years away. So that was one idea, but this is intended not for use on Earth, but for use in space, which is fine, but it doesn't help us here at the moment. So then, another idea which came from here, this is one of my colleagues here. In response to a query made to a colleague about the origins of a particular idea about the potential source of helium-3, I asked the question. He replied, the lunar helium-3 idea came not from a conversation, but arose very late night. One late night in December 1985, I was getting ready for bed, and after an evening of dealing with editing of a final report for the technical planning activity, a DOE exercise, it occurred to me that the moon had been collecting solar wind, including its helium-3, for billions of years because the moon possesses neither an atmosphere nor a magnetic field. Actually, both are there, but very small, of course. My wife woke up, and I told her I just had the strangest idea. The strange idea led to conversations with FTI colleagues and the inauguration of a new program for the Institute. Now, the sun is a very efficient fusion reactor. Frank, it's kind of annoying. You were trying to make the stuff on Earth. You go outside, there's this glowing ball that's doing it, and you know. Yeah. But, well, it turns out that some of the partial reactions in the sun, where you're at 14 million degrees, it says Kelvin. Frank, that doesn't matter what units, at that size, it doesn't matter what units you're using, Kelvin, centigrade, Fahrenheit, it doesn't matter. It's hot. And 3 million atmospheres in the middle, so it's high pressure. Some of the intermediate reactions you wind up with involve helium-3 output. So you're getting helium-3 generated in the sun. Some of this helium-3 leaks out of the sun and gets blown away in the solar wind, right? Now, we don't get this on Earth because we have a magnetic field which happily protects us from a lot of nasty radiation, and we have an atmosphere which also protects us. It also keeps us from getting helium-3 because it blocks it. So on the good side, we can live and exist because we have a magnetic field and atmosphere protecting us and breathe. But on the bad side, we can't, none of the stuff gets to us. So the solar wind is about 96% hydrogen ions and about 4% helium ions, and some fraction of that is helium-3. I don't know what fraction, honestly. But the estimate is the total helium-3 to hit the moon is about 500 million tons, that's metric tons, over 4.5 billion years. The moon has, again, a very, very weak magnetic field and an extremely thin atmosphere for all practical purposes, no atmosphere. So the solar wind can just slam right into the moon and into the regolith, as they call it, the lunar soil. And some of it just sticks there. So what happened is that when my colleague had this idea and they would talk about it, they went back to the Apollo data because all the Apollo missions took geology samples, and those samples were brought back to Earth, and there's a full assay done to find out what was in the samples. And sure enough, there was helium-3 in a very high concentration in those samples. All the Apollo missions, I believe, showed it, and as have a bunch of the Soviet lunar missions done with robots. They brought back samples from the moon. They all say the same thing. Lots of helium-3, which means you have approximately 1 million metric tons of helium-3 embedded in the lunar soil to a depth of 3 meters, right? About 10 feet. It's a lot of helium-3. So that would provide enough helium-3 to supply our electrical needs for 1,000 years. Right? That would be neat. And it's fairly easy to get it back from the moon once you mine it. So this would make the investment in the space industry program one of the largest payoffs in history. I mean, people complain about the cost of the space program, but if we do this, it's going to pay for itself many, many times over. So actually, we've actually been designing lunar miners to mine helium-3 from the moon, and these are various designs that have been come up with going back over some years now. Right now, there's a graduate student who's actually doing this work right now, doing experiments and planting and extracting gases from a simulated lunar regolith. So this is an active research program. Whether or not it will go any place, it's hard to say. It's a matter of will. But that's not the end of the story. There's more. Because once you have helium-3 on the moon, it can not only survive our electrical needs for up to 1,000 years, you can also provide resources for lunar bases and interplanetary flight. Because it's not just helium-3 that's buried in this lunar soil. You also have things like hydrogen, which can be used for fuel, water. There's actually water buried in the lunar crust in various places. Nitrogen gas, carbon dioxide, methane, carbon monoxide, things that can be used for life support. Helium-4, which is regular helium, good for cryogenics, and helium-3. So you process a lot of lunar regolith, you pull it into a miner, you heat it up, you extract the gases, bottle the gases, dump the old stuff out, and you can actually get quite a bit of stuff. And you can use the moon as a jumping off point for other planets. This would open up the solar system for us. So for example, right now, a manned trip from Earth to Mars would take, with a chemical rocket, would take several hundred days, a better part of a year, about 9 months to go from Earth to Mars. And if you're using a fusion propulsion system, the travel is reduced quite a bit. Similarly, going to Jupiter, the Jovian space, the trip time is reduced dramatically if you use fusion propulsion. Cargo transport, similar effect. You just have you can have a much higher payload fraction if you're using fusion propulsion than not. So if you have, of course, helium-3, you got that going. So helium-3 on the moon makes mining operations economically feasible. It enables lunar bases. It enables self-supporting space stations for various purposes. It provides fuel and consumables for asteroid mining operations. Asteroid mining would become practical. And a lot of all sorts of rare earths that can be extracted from asteroids, and then also provide other metals for constructions in space. It will also enable exploitation of the gas giants, especially Uranus and perhaps Saturn. The Project Daedalus was interesting to stop by Jupiter for the purpose of an interstellar flight. But you'd actually might be able to mine, believe it or not, mine the atmospheres of Uranus and Saturn. I say Uranus and Saturn because these planets are very light, relatively speaking, have a low density, so it's more feasible to go in, get something, and come out into the upper atmosphere. So this would enable interstellar probes and spacecraft that can reach the nearest stars within a human lifetime. And it could potentially provide Earth with enough helium-3 to meet all electrical demands at 21st century consumption rates for at least 1 billion years. I'm told this number's off by a factor of up to 100. It could be 100 billion years. But the fact is, once you get to this point, the problem's kind of solved. All right. So that's why I said at the beginning of this talk that this realization, this discovery of that the moon has helium-3 is something which should and probably will affect every man, woman, and child on this planet. Now, technology and discoveries like this don't make us better people. So whether it may affect us for the better or for worse can't be predicted necessarily, but at least gives us a tool where we can provide for the needs of mankind for a very long time, and we stop worrying about this. So the University of Wisconsin is playing a leading role in facilitating the eventual development of nuclear fusion power plants and in the near term, the development of nuclear fusion technology to solve or ameliorate a variety of immediate problems. And that's being done right here on this campus every day as we speak. Are there questions? Yes?
How close do you think we are to sustained nuclear fusion, confined nuclear fusion?
Well, we kind of already have that in some sense.
To generate power.
Yeah, but to get to the point where you'd be generating power, well, there are many frustrating things going on. Actually, one big frustrating thing is something called ITER, which is the International Toroidal Experimental Reactor built in France. It's an international effort, and that was supposed to be, and still is supposed to be, sort of the flagship device for the world fusion program. And at the rate they're going, they're not going to have first plasma until 2030 something, right? And this is supposed to be we're supposed to start doing the fusion reactors kind of operating in a somewhat sustaining mode and such. So I mean, if you go on the basis of that, we're probably looking at 2060, 2070. But as I said, there are private companies which are using other approaches and very agile, quick management models, which are building devices now which may actually work, or at least the chain devices which should result, probably quite likely result in a functioning reactor on a much shorter time scale. So I don't have my crystal ball or my tea leaves and my animal entrails with me to make predictions tonight. But I mean, I think sometime in the next 10 or 15 years, you're going to see something major happen from private industry. That's just my personal guess. It's no one's official opinion. But from what I hear, what I understand is going on, I think we'll see something. Now, when that gets deployed into, at the point it's going to be powering the grid in a big way, well, it's going to be some years after that. But it's on the way, I think, if we don't drop the ball and if these people persevere with their efforts. But it's private capital, and that's amazing. Because private capital is only attracted to things where there's some reasonable hope of a payback. So that means that people who are investing in these things actually think they're going to see a payback. And that's encouraging. Another question? Yes?
Which private companies are funding the construction of the fusion plants?
Well, I can't say all, but I do know that one major player that's operating in public is called Tri-Alpha Energy. And that's one that's actually come out in public and said things. And you can look them up on the internet and they'll talk about it. I think there are a couple others as well, but that's the one I know about. Yes?
You started out talking about fusing two, I can't remember exactly what they were, two things that ended up giving you high energy neutrons?
Well, there are two directions I was talking about, deuterium, and deuterium-tritium.
And then you went to helium-3.
Correct.
And so I got the impression at the beginning that there might be hundreds of combinations that could be fused. Do they all have either one or the other problem? In other words, it's neat that helium-3 works, but it's kind of unfortunate it's so far away. Is there another step up that doesn't have the neutron problem, but can be fused, that can be put in?
Well, one thing I should have pointed out, what I failed to point out in the lecture, is that the reason we're starting with these light elements like hydrogen and helium is that they have only one charge in them, one proton. So when you have like charges approaching, they naturally repel each other. All right. So the thing is, you've got to get these things which want to repel each other to get close enough to actually get within the capture radius and fuse. So hydrogen is simply the easiest way to do this. That's why the initial experiments are being done on for fission reactor, for the first generation of fusion reactors, you're concentrating deuterium-tritium mixtures because they are both hydrogen. They both have one charge, so they have the least problem fusing together. All right. That's why they're going that way first, despite the neutron problem. Helium-3 is helium, which has two charges. That means you're going to have much more Coulomb repulsion, and it's much more difficult to get the things close enough together to fuse. Yes, you can fuse other things. Let's say the thing ends at iron, right? So you can fuse anything under iron, as long as it doesn't add up anything beyond iron, it should work. But the bigger the nuclei are, the greater your atomic number, the greater that repulsive force is, and the harder it is to get these things to mash together. For example, there is one fusion reaction I didn't display was it's called p-boron 11. So boron, the same stuff you have in borax, right? Hydrogen, proton from water. If you can fuse them, that produces a low neutron reaction, which is also very good. But you have to, boron's a solid at room temperature, and plus it's got a relatively high atomic number, so you have even more repulsive force to deal with. That is going to be studied. In fact, I think we'll be studying here too if we have the time and money. But that's why we're talking about these light elements. It's just the easiest. That's the best place to start because you can make that happen more likely. Other question? Yes.
How do you transport neutrons?
You can't transport them.
So when you make them for medical purposes, does that mean the machine is there?
Well, what we do is what they're doing, and this is a Shine Medical. You can look up on the internet. They are building a plant in Janesville where they will have the neutron generator here, then they'll have the uranium slush around it in a solution, and then they pump, after as they've exposed uranium, they pump the uranium solution through, they extract the molybdenum chemical processes, and they put the rest of it back in the tank. Then the molybdenum is probably taken, put in a plane, and sent to whoever it's wanted, because it has a half-life. But they actually produce the radioisotope on the site and then get it to the hospital as fast as possible. That's what's being done right now, in fact, with the fission reactors. You produce it and then get it to the hospital as fast as you can, where the need is, hospitals. So that's why you have to have these plants near an airport, because you have to have a Learjet or something standing by to zip it off to the destination. Now, I mean, in fact, neutron physicists do kind of transport neutrons, since they can produce very cold neutrons and almost put them in a bottle, but that's way outside the topic of this, and nothing I'm dealing with. Yes?
So how would fusion propulsion actually work? You would have two containers, and you would have like an exhaust system, or?
Well, that would be, for example, you might have some sort of linear magnet arrangement. You inject helium-3 into this thing and heat it up, and then shoot some of it out the back end. The advantage of fusion reactions that they have, because the energies are so high, it has what's called a very high specific impulse, which is the equivalent of mileage for a rocket. Its technical definition would be the number of pounds of thrust produced per pound of fuel consumed per second. All right. So, and different fuel combinations have different specific impulses. But whereas a chemical rocket will have a number of a couple of hundred, this would be thousands. So that's why you can get a lot farther in a tank of fuel than you would with a chemical rocket. So I mean, no one's built one of these things. So how you actually do it is going to really not be figured out until we actually do it. But that's more or less what the approach would be. Other questions? Yes?
The so-called cold fusion discovery
Uh-huh.
a couple of decades ago, were they using helium-3?
No, they were using deuterium in palladium.
Rich, can you repeat the question?
Oh, sorry. The question was the cold fusion experiments of some years ago. Did they use helium-3? And the answer is no. They were using deuterium absorbed into palladium crystals, palladium cubes that were crystalline.
I believe that was at the University of Utah.
University of Utah, that's right.
And the cop came in and took them away.
Well, they did something. They did something which was very unwise. They got these exciting results, and instead of instead of putting it through peer-reviewed journals and being examined and critically examined, they took the results and they just went to the New York Times with it. Well, if you're going to do that, you better be right. And it turns out there are some mistakes in their experiments. It wasn't quite what they thought it was. As a consequence, they were disgraced. Now, we're onto something interesting. In fact, there's still people doing work with that, but it's not what they thought it was. And there are still things that will come out of that eventually. I'm not sure what, but it's an interesting laboratory phenomenon regardless. Any, yes?
What are the problems faced if you want to control the nuclear fission?
You mean fission or fusion?
Fusion.
Well, controlling is not a problem. The problem is making it happen. See, with nuclear fission, you put these fissile materials in a geometric arrangement, and it just works. I mean, it's spontaneous. You don't have to do anything. With a fusion reactor, you have to create the conditions to make it happen and maintain them. So the control isn't such a big problem, because if you screw up, it's just going to stop working. And that's really what the question is, not the control, but just making it happen, bringing about the conditions. Right? There's no China syndrome possibility of the nuclear fusion reactor. I mean, if it does that, it goes out of if you lose control of it and it, say, burns a hole in the vacuum tank, well, air can rush in and stop the reaction. You might have a lithium fire or something, but you're not going to have a nuclear meltdown. Any other question? Yes, back there?
Personal bias aside, can you give us your thoughts about the energy of the future and elaborate a little bit on it?
Oh, well, okay. I'm not particularly qualified to do that, but energy of the future is, unfortunately, determined by market forces, and sometimes bad decisions are made. For example, the Dominion nuclear plant, which is a perfectly good functioning nuclear plant, was shut down because the current natural gas bubble just made natural gas produced electricity too cheap to maintain it. So it's been shut down. But we're going to have fossil fuels, of course, for a time, and there'll be more and more work of solar energy and wind power and all these other alternate things which are good and we should have. There should be more nuclear fission reactors being built, and new breeder reactors being built, because I think that will sustain us for the next few hundred years at least, if this for the time being. I don't think we should turn our back on nuclear fission at this time. I think the technical problems are soluble. The political problems may or may not be. I think if we really put our minds to it, we could have nuclear fusion reactors starting up, within 10 or 15 years, but we don't have that kind of will yet. So at the current rate, it's going to be 20, 25 before you start seeing them being built and deployed. But once that happens, it's going to be very rapid deployment. The helium-3 fusion requires going to the moon and having a stable space program. I don't know if we'll manage that or not in the United States. The Chinese are very much focused on this. And in fact, the Chinese have been raiding our web server, which is physically located in my office, getting information about that for years. So they're very interested in this. And they're pursuing a very aggressive space program to go to the moon, and they intend to mine helium-3. So once someone does that, that will change the equation, especially if a functioning helium-3 reactor is designed and constructed and shown to be usable. Then that's going to take off. And so once you get into the next century, I think it's going to be helium-3 fusion will be sort of taking up everything eventually. Now, of course, this involves maintaining a supply line from the moon to the Earth. It requires a little geopolitical stability to do that. If I manage that, I don't know. As I say, technology doesn't make us better people. It just gives us more tools. But my prediction will be that coming into the next century, we're going to be seeing fusion reactors and the beginnings of helium-3 fusion reactors in large numbers. The original first fusion reactors will be deuterium and tritium, but they are going to be pilot reactors, demonstrators, and a few commercial plants. But they're going to be such a pain to maintain, I think, that they're not going to want to keep doing that, because the robotic handling of everything is just going to be a pain in the rump. But that's my own personal take on things. Yes?
Rich, I think there are international treaties controlling Antarctica mining there or not mining. Is there any international treaty controlling mining on the moon?
There is a space treaty on the moon, but the legal basis for that is that's still being worked out. We actually had a lawyer visit us a few years ago, to actually talk about the possibilities of a moon mining treaty. And they're thinking of basing this on the law of the sea mining treaties. And I have no idea where that's going to go yet. That's going to be a little, there's a lot of negotiation, because the fact is only a few nations are going to have the capacity to go to the moon and mine. So the question is, well, okay, if this is a resource for all mankind, how do you distribute it? How does all mankind benefit from this, and not just the countries that can actually go there and get the stuff? And that'll be a political issue in the future, I'm sure. Since we can make political issues of anything, and I'm sure it'll be very critical. Any other questions? Yes?
Is anybody working on a way to make helium-3?
The only way to make helium-3 is to produce tritium and let it decay. And that's how we do it now.
You can't take helium-4 and strip off the electrons.
Well, that would be, it would take too much energy to do that, yeah. Any other questions? Yes?
There have been some efforts using lasers to explode deuterium pellets.
Yes.
Is that research still going on?
Oh, yes, it is. I didn't go into that too much because we have a UW focus, but the National Ignition Facility in Lawrence Livermore Laboratories in Livermore, California, is working that. They have a huge machine built with huge rooms full of lasers that all focus inside of this evacuated sphere. All these beams of laser light, which are very short pulse, are aimed at a teeny tiny pellet of deuterium tritium, which is located inside of a little tiny gold-plated can. So the lasers hit the inside of this can from top and bottom. They strike the inside of the can, generate X-rays. The X-rays then come in and compress the pellet. They were actually very close to getting to a substantial break-even, but then weird things started happening they didn't anticipate. As the lasers are coming into the plasma that was forming, energy was being transferred from one laser beam to the next inside the plasma, making an asymmetric explosion. So that caused a problem. So I think they got around that finally. But there are all sorts of physics. When you compress a pellet like that, the stability of the pellet as it accelerates in is key. So if it starts getting rough, if it's not smooth enough as it accelerates in, then you don't get enough compression and it fails. But they've had very promising results. That's going to continue. The question is, if they actually manage to get break even, and much more than break even, then how do you build a power plant with these things? Because this is a huge laser setup. I mean, it's look it up on the internet. It's mammoth. And the fact they actually get this thing to work and work reliably is a testament to the engineering skill at Livermore Laboratories. It's incredible. It really is incredible. But whether or not they'll ever produce a commercial reactor, I don't know. But that is being researched there, and I think also at Cornell University and a few other places, laser fusion. Any other questions?